Good morning, everyone. If someone can confirm that you can hear me, then we can get started. Okay, Ms. Leong says you can hear me, so all good. So just a few admin comments before we get started. The web work exercise set 1 is open. It opened at 10 a.m. yesterday morning. Given that I haven't received any serious issues around accessing it, there was one email from Mr. Nika, which I think sorted itself out. His situation sorted itself out. Given that there was nothing else, I assume that everyone's logged in and working on the exercise set. As I indicated in the announcement, these web work marks will contribute towards your semester mark. So please make sure that you do as many of them as you can. What I plan to do is something similar to what we did for 1B, where we will have 1 or 2 extra for the semester. So if you miss 1 or 2, then you won't be negatively affected, which means if there's a week that you're sick, then you can skip doing your web work assignment or assessment that week. So definitely we won't have more than 2 to spare. So by the end of the semester, I hope that we would have done 8 or so of these weekly tests, and then I will use 6 of the marks. Right. The tutors are now on board. I have email addresses for them. I'm going to post an announcement and update the study guide with their details. So you've got more people that you can email questions to. In addition to that, 1 or more of them will potentially do the Wednesday tutorial slot. So one of the tutors will sit in tomorrow to see what I do. And tomorrow is also going to be important because I want to test using a writing pad. Instead of us just talking about the solutions, I've set up some more software that allows me to write through solutions a bit closer to what we would have in a normal tutorial session. So please come along tomorrow. It's the double period again. And then the last thing is I had one confirmation message on the discussion forum that in fact the recording that I loaded on Friday did work. So if you haven't yet and you do want to check it out, please double check that it works. If you've downloaded the file and tried it previously and it didn't work, rename the file with a .mp4 extension. Then that sorted it out and it played on my laptop, which is a Windows 10 laptop, and I used Windows Media Player to test it. So please double check it. What I'd like is for the recordings the additional recordings that I'm do to be available for you to be played on a smartphone, for example. Then more people can make use of the recorded lectures. Do keep in mind, if that works, we can't have both because it takes quite a bit of time. So if I start recording the lectures, I'll post them so that they are available for you in this slot. And then in this slot, you can download it and watch it and have a 45-minute period in which you can listen to the recorded lecture. Okay, I'll look at one question from Kumari. LMJ Kumari says, just to clarify, sir, we only have the web work exercises and you'll announce when we'll have a class test that counts towards the semester mark. Okay, so that is correct for now. So we have the option of doing both. We have the option of doing both web work exercises and Blackboard quizzes and we can use both marks to contribute towards the semester marks. The webwork exercises, the webwork as a platform is better in this environment for me because it allows me to set up things you have to calculate. Okay, someone has just logged in and you need to mute your microphone. Okay, please mute your microphone. Okay, so Komari, yes, but we could use Blackboard exercises as well. When there's a Blackboard exercise, then I will post the announcement. Okay, there's a question, am I the only one whose webwork link doesn't work? So the webwork link, if the link doesn't work, then I don't know what the problem is. If you can see the interface but you can't log in, then chances are you are not configured on the system. And this is possible if you've recently joined the module. If you joined the module in the last 2 days or so, then your name won't be on the database. Then you need to send me an email. In fact, I will post an announcement. The email doesn't come to me. I'll post the announcement with the details for the person you need to send it to. This exercise set will be open until Sunday at 10. So you do have a little bit of time, but don't waste your time. Send the email today as soon as you see the email address. Okay, we've spoken quite a bit. This lecture is going to be a little bit shorter. We're looking at section 11.3, and I'm going to switch over now and share my screen. Okay. There was one question that came up. I just want to handle that one quickly. It says, when I tried login from Blackboard, it doesn't work. It works when you open the link on a new tab. Okay, cool. So there's a potential solution coming from ZM Rakaza. Okay, thanks for that. Okay, I'm going to share my screen and we get started with the work. So the good news, a little bit of good news is that, sorry about that. This section is a little bit shorter than the other ones we've had so far. So there's a bit less rush to get through it. So I'm going to do half of it today and half of it on Thursday night again. And the part that I'm going to do today will go up to the end of example 4, hopefully. And because we've got the little bit of extra time, I'll do example 14 from section 11.1 probably and post a recorded video for that. Okay, so let's get started. So now we've spoken about, in week 1, we spoke about sequences. In week 2, we spoke about series. And of course, the whole concept of a series is built on the concept of a sequence. You must understand the first to understand the second. And then we said sequences and series are all well and good, but really the only ones that are of any interest and any value to us are ones that converge. So an infinite series is an infinite sum of terms, and many of these can be made to have a finite number as a sum, right? And we've seen examples last week. And now we are interested in finding out, number one, when a series, how do we know that the series converges? And how do we know what its sum is once we know that it converges? Well, it turns out that it's actually quite difficult to find the exact sum of a series, okay? The ones that we looked at, the examples were geometric series, where the common ratio is in between negative and positive 1, not including the endpoints. Those ones converge, and we've got a formula for calculating them. But that's actually almost as good as we can do in terms of calculating sums. Then there are other series, like the one you see on the screen now, the sum of 1 divided by n times n plus 1, where if you write it out, then you can see that the middle terms do that collapsing effort, in which case it's easy to calculate the limit of the the limit of the partial sum as n goes to infinity. Right? But outside of that, it's usually, outside of those two kinds of series, it's usually quite difficult to be able to calculate the sum of a series. Right? And so in this section, we look at one theorem that tells us how to identify series that converge. Okay, and the methods that we use will be based on improper integrals. So you'll remember from the 1A module in section 7.8, we had the concept of an improper integral, and that was an integral. There were two types of these integrals. The first one was where you had a number as a starting point and you integrate it to plus infinity. And that's the kind that's going to become useful for us. So I'm going to do two examples, which the textbook also does. I've added some more details and I've numbered them so that when you go through the notes, you pay particular attention to them. They are important and they justify or explain where the test comes from. Okay, and the test is called the integral test. We'll see it in a minute. Okay, so let's look at the series below. The series is the sum from 1 to infinity of 1 over n squared. And because we're summing to infinity, we're going to sum all of the terms for every positive integer n, right? And when we expand that, you know what that shorted writing on the left-hand side means. It means 1 divided by 1 squared plus 1 divided by 2 squared and so on. Right? Now, we want to investigate whether that series converges or diverges. And we're going to do it by comparing it with an improper integral that we did in section 7.8. And that improper integral was also one of the sort of introductory examples in that section. And that integral turned out to be, remember, we define, okay, let me see, there's many comments coming in. Let me just make sure it's not something I have to pay attention to now. Please try zooming in because I cannot see the slide clearly. There's nothing I can do if you can't see it. I can just share it again. If you can't see, then potentially the problem, if there are many people who can see and you can't see, then the problem is with your network. Am I the only one who can't see the series? Same here. You were the one who's supposed to zoom. I also can't see. Okay, I'm going to reshare and hopefully this time it goes better. Okay, so let's try it again. Okay, if everything's quiet, I'll assume that everyone can see. Okay, so we're going to investigate whether the series below converges or diverges. Right? Now, when we do that, we're going to compare it with the infinite integral, the improper integral that you see on the screen, the integral from 1 to infinity of 1 over x squared dx. And that integral turned out to be equal to 1. Right? Remember what we did in that section. We defined what we meant by an integral where infinity is one of the endpoints to be a limit. We integrated it to a point t and then took the limit as t goes to infinity, right? Now, let's see what happens now. Now, let's look at the diagram below, okay? So, if you look at this diagram, notice that each of the blue rectangles has a base equal to 1. So the base of the blue rectangle where it says area equals 1 over 2 squared. That the base is 1. Now, why is the area equal to 1 over 2 squared? Well, look at the graph y equal to 1 over x squared. The right endpoint of that second rectangle is at 2. And so the value of that function y equals 1 over x squared is to be read off where that rectangle cuts the curve. And so it makes sense. Also notice that because the base has length 1, the area of a rectangle is base times height. And so because the base is equal to 1, the area of that rectangle is really just 1 over 2 squared. It's 1 over 2 squared times 1, which is 1 over 2 squared. And that's one of the terms in the expansion of that series, right? The next rectangle is the next term, and the next one is the next term, and so on. Now notice, above each of those rectangles is a little bit of a white area, almost triangular white area between the rectangle and the curve. And so that means if I take the infinite sum of all the rectangles and I integrate that function 1 over x squared from 1 to infinity, remember what the integral of a function is. It's the area under the curve, which means the area under the curve must be larger than the area represented by the infinite sum of the rectangles. But the infinite sum of the rectangles is exactly the series that we're looking at, right? And so we know that the sum, now notice when we do the sum, we've ignored the first rectangle. So forget about the first rectangle for now, right? The rectangles will go from the second rectangle. And so the sum from 2 to infinity of 1 over n squared must be less than the integral from 1 to infinity of 1 over x squared. And now I can simply add a 1 to both sides of that inequality. And I get 1 plus the sum from 2 to infinity is less than 1 plus that infinite integral, which is 2. 1 plus 1 is 2. And so I know that the series, the sum from 1 to infinity of 1 over n squared, that must be less than 2, which means I have a sequence of partial sums which is bounded above by 2. Also, if you go back to the diagram, each of those terms in the expansion of the series is a positive number, right? Because I'm squaring it. I'm adding positive numbers, which means that sequence of partial sums is monotonically increasing. It's a monotonic sequence. And because it's monotonic and bounded above, we can use the monotonic sequence theorem, and we can conclude that the series must converge. So there's our first example of seeing how we can use the tools that we have to figure out whether a particular series converges or diverges. This one converges. We can say a little bit more about this series. Now notice that we have not calculated the sum of the series. And in fact, it's not easy to calculate the sum. The sum has been calculated by quite a famous Swiss mathematician, a man called Leonhard Euler. Okay? And he calculated the sum in the 1700s, if I remember correctly, 17 or early 1800s. And the sum comes to pi squared over 6. So if you want to follow along a set of problems that leads you to constructing this answer, look at problem 6 in the Problems Plus following chapter 15. Okay, so that's the first one. Let's look at another one. Let's look at a series that diverges and how we can use an infinite integral to prove that it diverges. Look at this series. The sum from 1 to infinity of 1 over the square root of n. Now, it's not n squared, it's the square root of n. So it's 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, and so on, all up to infinity. And again, we're going to use a diagram, and we're going to use this diagram where, again, we've drawn rectangles of base 1, and we've drawn the curve y equals 1 over the square root of x. Now, notice, in this case, if I want to calculate the height of a rectangle at an endpoint and compare it with the value of the function, then in this case, I need to use left endpoints. So the value of the function at 1 is the height of the first rectangle. The value of the function at 2 is the height of the second rectangle, and so on. And again, because the base has width 1, the height of the rectangle is equal to the area of the rectangle, but it's also equal to one of the terms in the expansion of that series. And so now we can compare it with another improper integral. We can compare it with the integral from 1 to infinity of 1 over the square root of x dx, which we know from section 7.8 diverges. And in this case, I've explained all that. In this case, it's easy to see that the sum, the infinite sum, must be larger than the integral. It's easy to see because in this case, the area, because in this case, there's a little bit of area above the curve, which is still enclosed in the rectangle. See, there's no white bits where the curve is higher than the rectangles. It's the other way around here, which means the infinite area represented by the rectangles must be larger than the area represented by the infinite integral. And since we know the infinite integral diverges, the sum must also diverge. It cannot converge to a finite number. Okay, so these two examples have sort of justified the following integral test. We'll look at the test, we'll explain what it means, and we will do the proof. The proof is based on similar arguments as what you've seen with these rectangles compared to the area under a curve. So let's go. Suppose that f is a continuous, positive, decreasing function on the interval 1, infinity. And let an be equal to f of n. Then the series, the sum from 1 to infinity of an, is convergent if and only if the improper integral, the integral from 1 to infinity of f of x dx, is convergent. So now this is an if and only if statement, which essentially means we can replace convergent and divergent. In other words, we've got two statements here. If the integral from 1 to infinity of f of x dx is convergent, then the sum from 1 to infinity of an, in other words, the series an, is convergent. Alternatively, if the integral from 1 to infinity of f of x dx is divergent, then the series is divergent. Right. So the integral test, the first of the tests that we'll do a number of others in the module. The first of the tests that we'll do to determine whether a series is convergent or divergent. Let's prove it. Okay, As I said, we're basically going to use a very similar argument to the one that you've seen already in example -1 and example 0. So consider the diagram above. Now, the area of the first shaded rectangle is the value of the function at the end of the interval. Right? So the area of the first shaded rectangle, there the area is indicated as A2. It's the value of the function at the end of the interval. In other words, f of 2 is equal to A2. Now, the fact that it's the area is equal to the value of the function comes from, again, the fact that the base of that rectangle has width equal to 1. Area is height times base. Right, move on. Now, this is also obviously the case for all the others. So the area that's marked A4, for example, right, that area is given by the height of the function, by the height of the rectangle at the point 4, the x-coordinate 4, which becomes the value of n equal to 4. And when I calculate that, notice it's the value of the function read off on that curve. Right. Now, comparing the areas of the rectangles, the shaded rectangles, with the area under the curve, it's obvious to see that if I integrate from 1 to n, I'm not integrating to infinity. I'm integrating from 1 to n of f of x dx. Then the area under the curve, right, must be larger than or equal to the sum of the areas I've just indicated. Must be, because of the little white bits that are above each of the rectangles. So this inequality, this is very important. This inequality depends on the fact that f is decreasing. So in this picture, the fact that we have to use the right endpoint to get this inequality comes from the fact that the curve is decreasing, the function is decreasing. Now, look at another diagram. Reasoning in the similar way, we get the fact that in this case, the integral from 1 to n of f of x dx must be less than or equal to, again, we integrate from 1 up to n. The same curve, 1 equals f, from 1 to n of f of x dx, this must be less than or equal to now the sum of areas of rectangles starting from A1 up to AN minus 1. So we've got these two inequalities, inequality 4 and inequality 5. Now we say, let's suppose that the curve is such that the integral from 1 to infinity of f of x dx converges. Then we can use 4, right? Now we know that that integral converges, the integral on the right there. And we can use 4 to say that the sum from 2 to n of ai is less than or equal to the sum from 1 to n of f of x dx, and that must be less than or equal to the infinite integral, the improper integral, right? And so I can construct now my partial sum. Remember what the partial sum is. The partial sum is the sum up to n terms. All I need to do is to add a1. For inequality 4, we didn't have a1. We started at a2. And so we've got a1 plus that sum up to n terms starting at 2 must be less than or equal to a1 plus the infinite integral, which we know converges. So that's a number, which means Sn, the partial sum up to n terms, must be less than or equal to m, some number m. We don't care what it is. We know it's a real number because we know a1 is a real number, and we know that that infinite integral, that improper integral converges. So that's a number. And so we've got m, which means Sn is less than or equal to this number m for all n. It means the sequence of partial sums must be bounded above. And because it's bounded above and it's increasing, it's monotonically increasing because the areas are not zero and not negative. They're always positive. That means we've got an increasing sequence bounded above. We use the monotonic sequence theorem. It must converge, hence the series must converge. What about the other option? Suppose that integral is divergent. Well, then we use inequality 5. We say, we know then that the integral from 1 to n of f of x dx becomes larger as n becomes larger. And because of that, we can start with inequality 5. Let me take you back to it. Here's inequality 5. Inequality 5 has the integral from 1 to n of f of x on the left of the sum from a1 to an minus 1. And so we start with that. Since we're assuming that the infinite integral, the improper integral, diverges, we know that the integral from 1 to n of f of x dx grows larger as n grows larger, because f of x is greater than or equal to 0. But from 5, we know that the integral from 1 to n of f of x dx is less than or equal to the partial sum up to n minus 1 terms. And so, since the integral from 1 to n of f of x dx becomes larger as n becomes larger, we must have that Sn minus 1 becomes larger as n goes to infinity. This implies that Sn becomes larger as n goes to infinity. And so the sum of an diverges. That series diverges. So let's look at the statement again and then move on. There's the proof. You must know the proof. So in this environment, it's a bit of a challenge for us as lecturers to test your theory. But we have to. So I probably won't ask you to reproduce the integral test as is, but I will ask you questions in the semester test to test whether you understand why this integral test works. The same for all the proofs that we do. So here we go, the integral test. Suppose that f is continuous, that it's positive, and that it's decreasing on the interval from 1 to infinity, and let an be equal to f of n. In the series, the sum from 1 to infinity of an is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. So if you think about it, this if and only if statement is really two tests bundled in one. If, and it works like this, if the integral from 1 to infinity of f of x dx is convergent, then the series an is convergent. If the integral from 1 to infinity of f of x is divergent, then the series from 1 to infinity of an is divergent. Okay. Let's look at some notes and look at some examples. I'm actually going a little bit too slowly, so I'm going to speed up a little bit. Okay, so the first thing to note is when we use the integral test, it is not necessary to start the series or the integral at n equals 1. For instance, in testing the series, the sum from 4 to infinity of 1 over n minus 3 squared, we use the integral from 4 to infinity of 1 over x to the 3 dx as the function that we compared with. there should be a square there, right? Also, it is not necessary that f be always decreasing. The point is f must be decreasing from some point onwards. So it can't do what the sine or the cosine function does, where it's increasing, decreasing, increasing, decreasing, changing infinitely many times. So the function could be increasing up to a point, and after that it's always decreasing. Then you can still use the integral test. If you think about it, whatever happens under the curve from some starting point, as long as the function is continuous, in other words, that it has no points where it spikes up to infinity, as long as it's continuous, then the area from some starting point till the end of the interval where it increases is finite. And so it doesn't affect the final answer. So think about these things carefully. I think there's a mistake here. I think the 1 over x minus 3 in the second expression should be 1 over x minus 3 squared. Okay, I'll fix it. And I'll double check that it's not there in the notes. I'll post the notes after this lecture. What is important is that f is ultimately decreasing. That is decreasing for x larger than some number n. Then the sum from n to infinity of an is convergent. Hence, the whole series must be convergent by a note in the previous section. Remember, we said that a finite number of terms doesn't affect the convergence or divergence of a series. And if you think about it carefully, you should be able to see that that's the case. It's not something you should memorize. Okay, let's look at one. Let's look at an example. Test the series, the sum from 1 to infinity of 1 over n squared plus 1 for convergence or divergence. The function f of x is equal to 1 over x squared plus 1 is continuous, it's positive, and decreasing. Notice that when I'm tackling the problem, I need to double check explicitly that the function that I use satisfies the conditions of the theorem. So I say it explicitly, and this is what I expect you to do in answering questions. The function f of x is equal to 1 divided by x squared plus 1 is continuous, it's positive, and it's decreasing on 1 infinity. And so we are allowed to use the integral test and say the integral from 1 to infinity of 1 over x squared plus 1 dx is the limit as t goes to infinity of the integral from 1 to t of 1 over x squared plus 1, which is equal to, you'll remember that the antiderivative of that expression, 1 over x squared plus 1 dx, or 1 over x squared plus 1, the antiderivative is the arctan function. And if you don't remember, go remind yourself. Right? You have the textbook, go look it up. So that gives us the limit as t goes to infinity of arctan x evaluated between 1 and t. That means we plug in a t, arctan t minus arctan of 1. Well, arctan of 1 is pi by 4 because tan of pi by 4 is 1. And we let t go to infinity, and we get pi by 2 minus pi by 4, which is pi by 4. And because we get a finite answer, a finite number, it means that the improper integral is convergent. And so by the integral test, the series must be convergent as well. Right? Let's see how we go, how far we get with example 2. For what values of p is the series the sum from 1 to infinity of 1 over n to the p convergent? We'll do a few minutes and then we'll stop. If p is less than 0, then the limit as n goes to infinity of 1 over n to the p is infinity. So by now, you should be able to, you should remember these things or develop a feeling for them. If p is equal to 0, then the limit as n goes to infinity of 1 over n to the p is 1. That should be obvious because when p is equal to 0, the expression just becomes 1, right? So it's 1, 1, 1, 1, 1, 1, right? Now, in either case, we have that the limit as n goes to infinity is not 0. Hence, the given series diverges by the test for divergence. So remember, the integral test is really the second test we've done. It's not the first one. We had the test for divergence, which was the contrapositive of another theorem we had. What about the case p greater than 0? Well, in that case, it is clear that the function f of x equals 1 over x to the p is continuous. It's positive and decreasing on 1 infinity. And in chapter 7, we found that that integral, the integral from 1 to infinity of 1 over x to the p dx, converges if p is greater than 1, and it diverges if p is less than or equal to 1. It follows then from the integral test that the series, the sum from 1 to n to the p, converges if p is greater than 1 and diverges if p is in between 0 and 1. Now, these series are called the p series, right? Notice also that when p is 1, we just get the harmonic series, which we know is divergent. This p series is important, right? It will come up all the way through the rest of the module. I think we'll stop there. We'll continue Wednesday night. I'm going to stop sharing because I want to have a quick look at any questions that came up. There's only one or comment. And actually, there was nothing else. Can the harmonic series be considered monotonic? The harmonic series, yes, the harmonic series is a monotonic series. It's increasing, right? But it's not bounded above LMJ Kumari, just in case you were wondering. Another question. We have probably about 30 seconds left. 55. Nice, we had a nice turnout. We had 55 people. So thanks. I will see you tomorrow morning. We'll have a tutorial session, a double period, where I'm going to test out my writing device because I've had a few requests for us to write and not just talk, which is good. We'll see how that works tomorrow. And on Thursday evening, we'll have the second half of this lecture. Okay, thanks for coming. Go and do some maths.